In our last video, we're going to discuss the transpose of a matrix. And here's the notation here. So here, the transpose is very simple here. So suppose we have an M by N matrix, A. We define the transpose of A, and it's denoted as A where there's a T for transpose in the superscript to the right of it. This is not at all an exponent. This is just notation here for the transpose. If you're looking in some other textbook or some other context, you might see a superscript lowercase t as well. Either a lowercase t or an uppercase t is the two different notations that I've seen for the transpose. Okay, so here's how it's defined. It is an N by M matrix whose columns are formed by the corresponding rows of A. What does that mean exactly? Basically, if you take the rows of the original matrix A, they're going to be turned into columns in the matrix A transpose. Let's go ahead and work out an example and see what this looks like. Okay, so what is A transpose if this is the matrix A? So basically, we're going to look at the two rows that A has. And so the first row is going to become the first column in that new matrix. And then the second row becomes the second column in that matrix. And that's it. It's really as simple as that. Okay, so let's do another example. So suppose this is our matrix B. So let's pick out the rows. There's 3 rows here. Okay, so B transpose, so our first row is going to become a first column. The second row becomes the second column. And then the third row becomes the third column. And that's B transpose. Simple as that. All right, let's look at some properties of this new operation that is being performed on matrices. So we're going to assume that A and B denote matrices whose sizes are appropriate for the following sums and products to be defined. All right, so it turns out that if you have A transpose and take another transpose, you get back to the original matrix A. It makes sense if the rows become the columns when you take the transpose. Then when you take a second transpose, you're going to go back to the original matrix if you just think about what this is doing here. Okay, how does the transpose interact with matrix addition or summation? Well, you can basically just distribute it. So if you could add the two matrices together first and then take the transpose, or you take the transpose of each first and then add them together. And then third, how does it interact with scalar multiplication? Well, it turns out it's very easy. You can either do the scalar multiplication first or you can do it afterwards. It doesn't matter. And this should, again, make perfect sense if you think about what's going on with A transpose either being A transpose being done first or A transpose being done second. Since scalar multiplication is done entry-wise, you'll end up with the same thing regardless of which way you choose to do it. The last one shows that there is some subtlety with the transpose. Again, you got to slow down when you do matrix on matrix multiplication. You can't just distribute the transpose to each one. Basically, B transpose times A transpose is going to be the same as if you were to do the matrix multiplication first and then take the transpose. That's the same as swapping the order of the matrices and then taking the transposes. So you got to really slow down and think about that property. For our last example here, we're going to look at the subtlety of the transpose mixed together with matrix multiplication. Okay, so we're going to compute the following 4 quantities. So suppose we have these 3 column vectors, these 2 column vectors, u and v. We're going to compute these 4 quantities and see what they are. Now, these are technically vectors, but you can think of them as being matrices. You can think of any vector as being a matrix. So this would be a matrix with 3 rows and 1 column. Same goes for this. So we already know how to do all of this stuff, but let's go ahead and work this out to see some of the subtleties. Just to save a little bit of time in this calculation, and again, this is something we've already done here before. So if we were to do U transpose V, U transpose, it was a column vector to begin with. Now it becomes a row vector. And if you do the matrix multiplication, what do? You're going to take your first entry, turn, match it up, multiply with, oh, excuse me. Yeah, here, let me back up. Let me try that again. So we have our first row. Yeah, I like this better. So let's take the first row, turn, match it up with the first column, multiply, add them up. Here's what you would get. If you've taken Calc 3, you already know what this is. So U transpose V is simply scalar, a scalar product or a dot product, or as we'll see later in the class, we actually call this an inner product. Now, V transpose U is the same type of thing. We're just doing things in a different order. So you do that matrix you do this matrix multiplication, turn, match it up, multiply, add them up, and you end up the same thing. So these two quantities are actually equal to each other. U transpose V is the same as V transpose U, if you're talking about column vectors. And both just represent the dot product. And you've seen, so this is a new way of defining the dot product or the scalar product. And you saw in Calc 3 that the order in which you do this doesn't matter. And this just shows this in a different way. Okay, so this is what we've shown here. Now let's do the other two. If we had U V transpose, this is the column vector U. Here is V transpose right here. Now things are different. You take your first row, turn, match it up, multiply with the first column, and then the answer goes right here. Now you move on to the second column, and then do the multiplication, add them up, your answer goes right here. And then you just kind of continue along and notice what you get. You end up with a 3 by 3 matrix. And if you're just looking at the size of things, this was 3 by 1 to begin with and 1 by 3. The 1s match up, which means you can do the matrix multiplication, and the 3s on the outside tell you the size of the resulting matrix. Okay, so what if we were to do V U transpose instead? Well, this is what it would look like. And if you, just like we did in the previous here, if you go ahead and do that matrix multiplication, this is the matrix you would get. Notice that these two are not equal to each other, but they're actually transposes of each other. If you take the transpose of this, you would end up with this. And that's just simply because we have this being true. Go ahead and use that property that we had in the previous slide. If you distribute the transpose, you have to change the order of the multiplication. Something is not right here. Oh, it was U transpose transpose, excuse me. Here, U transpose transpose. Change the order, V transpose. U transpose transpose just becomes U, and then this is V transpose. So notice the two are equal to each other. Okay, so I think that officially finishes up the section. Yes, that's right. So we have finished 2.1. You can finish up all the remaining MyLab homework problems. Here's a summary of what it is that we talked about. So we have three or four different notations for writing out a matrix. One that emphasizes the columns, one that emphasizes the entries, and one that is kind of compact. And then we had some addition and scalar multiplication properties right here below. And basically, when you're doing addition and scalar multiplication, you do so entry-wise. The transpose is basically taking the ith rows and placing it into the ith column. And here's some of the properties that go along with that. Matrix multiplication. Here's the properties. Here's how you do it. So basically, it corresponds to the composition of corresponding linear transformations. Here's how it was defined in the textbook in terms of matrix on vector multiplication. Here's kind of a shortcut formula that we used for a couple examples. And then, like I said, here's the properties kind of involving that. Oh, and I'm seeing a typo right here. This should actually be B plus C right here. if I squeeze that in there, B plus C. I'll fix that for your notes. Okay, and then these are things that are not properties. You have to be very careful, because it's very tempting to just think about working with these new objects with the rules of algebra that you learned for real numbers, and these three properties do not hold. Okay, so we've officially finished up section 2.1.